Here we have a whole bunch of atoms of two different types. And it tells us information about the potential energy of, looks like this solid curve represents potential energy of an AA pair or a BB pair. Those would be identical. And then this dotted line tells us information about the potential energy of an AB pair, so a mismatched pair of atoms. And we want to, what are we trying to do here? If we have this chain of 100 such atoms. What's our goal here?
Probably to figure out like Ebond.
Sorry, what was that?
Maybe to figure out Ebond.
Yeah, we want to find the bond energy of the whole chain, right? And it's not just these four atoms shown, it's 100 atoms, presumably 50 A atoms and 50 B atoms.
Mm-hmm. So
we want to figure out the total bond energy of that entire chain. Well, not the exact entire bond energy. We can round it off. We can estimate by looking at just the bonds that are less than or equal to 2 R naught apart from each other. So that would be, for example, what would be one type of bond we would need to include there?
Nearest neighbor.
What was that?
Nearest neighbor.
So like what types of atoms then?
So the AB atom.
Yeah, it looks like the closest bonds would be bonds from A to B. So if we consider a typical AB bond from A to B, and note that that's distance R naught, so that's less than or equal to 2 R naught. That is the sort of bonds we're trying to include here. That AB bond, how would we figure out the energy of one of those bonds?
With the graph?
Yeah, if we take a look at the graph, this is R naught apart from each other. So where on the graph should we look to figure out that energy?
Maybe where it says like PE of AB.
Sorry, could you speak up a bit? I couldn't hear that.
Yeah, so probably where it says AB, like potential energy of AB.
Yeah, we definitely want to look at the potential energy of AB curve because this is a bond between A and B. And specifically, where on that curve should we be looking?
Oh, the lowest point.
Yeah, if these are exactly R naught apart, that's the equilibrium distance. So that is the lowest possible potential energy, which looks like, what is that? Maybe, is that 3? 3. Yeah, I think that's negative 3 times 10 to the negative 21 joules. So we can use that as, and for now, we might want to just call it epsilon. So let's use epsilon as an abbreviation for that. We'll say for AB bonds, epsilon is, looks like 3 times 10 to the negative 21 joules. And we're going to call epsilon a positive value. It's just that the potential energy is negative epsilon, negative that value. So we'll just call that epsilon sub AB. Then the potential energy of one of those bonds would be negative epsilon AB. But we're not dealing with just one bond. How can we figure out how many bonds of this type we're dealing with? If we've got this cluster of 100 atoms, how would we figure out how many AB bonds there are?
You can just probably divide 100 by 2 to get like 50 AB bonds.
Would that work? If we have, like, let's try that on this smaller cluster. Looks like we've got 4 atoms. If we just look at this, just what's pictured, we've got 4 atoms. How many bonds do we have?
Oh, is that 3?
Yeah, it looks like we've got 3 AB bonds. So 4 atoms would lead to 3 AB bonds.
Mhm.
Let's try that with, so it's definitely not just a divided by 2 thing. Let's try a few more bonds and see if we can establish a pattern here. Let's say we had something like, let's say instead of 4 such atoms, we had let's have a few more atoms, maybe 2, 4. Oh wait, I'm gonna have to modify that a bit because we want them to alternate. So AB, 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 AB. So that's 2, 4, 6, 8, 10 atoms. If we actually count up the bonds, because this is still small enough that a small enough sample that we can do that. So counting them up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds. Anyone want to make a guess as to how many bonds 100 atoms would have? Yeah, it should be 99. Because if you've just got a chain of atoms lined up and you're talking about all the nearest neighbor bonds, looks like there should be exactly 99 of those, one less than the number of atoms. Because for instance, the first atom is connected to the second, second is connected to third, third is connected to fourth, and so on. But the last atom is not connected to the last plus 1 atom. There is no last plus 1. So it looks like if there's 100 atoms, there should be 99 nearest neighbor bonds. So how would we figure out the potential energy of all 99 of those bonds? We've got 99 bonds, and each one has this much energy. What could we do to get the energy of all 99 bonds?
You would just multiply.
Yeah, we can just multiply that. 99 bonds times negative epsilon AB. That'll tell us the total energy of all of those, all 99 of those bonds. So that'll be negative 99 times epsilon AB, which was 3 times 10 to the negative 21 joules. 3 times 99 would be 297, so negative 297 times 10 to the negative 21 joules. So that would be the energy of all of the AB nearest neighbor bonds. Any questions on that so far? So now that we know the energy of all of the AB nearest neighbor bonds, what other bonds do we need to consider? What do you mean by NNN? Which bond, like what would be an example of the bonds we're also looking at? Like from what to what? Yeah, if we take a look at the AA and BB bonds, let me clear out the AB bonds we were just looking at. So if we're looking at an AB or AA bond or a BB bond, let's take a look at those individually. Let's say we're looking at an AA bond. What's the actual distance from an A atom to the next A atom? Yeah, that's 2R0, which is still within the scope of what we're trying to find. That is less than or equal to 2R0. But anything further than that, we're going to ignore. It still technically contributes to the bond energy, like for instance, from this A to this A. That is a bond that contributes to bond energy, but it's a much weaker bond because they're so much further apart. So the potential energy is very, very close to 0. So we're going to ignore anything that's further than 2R0. But that does mean we need to include all of the A to the next A bonds and all of the B to the next B bonds. So let's take a look at just from A to the next A. I'm going to put this to the side. We can come back to that later. So if we look at just the A to the next A bonds, how would we figure out the energy of one of those bonds? Can we still use our graph here? Yeah. Instead of using the dotted line graph, we're going to use this solid line graph because we are talking about AA rather than AB. But they're no longer are not apart from each other. So we're not going to use the low part. We're going to have to use what R value instead. What's the actual distance from an A atom to the next A atom? Yeah, 2 R naught. So if we go back to the graph, it looks like R naught, as usual, is about 1.12 sigma, where sigma is the atomic diameter, 10 to the negative 10 meters. So if we want to double that, we'll go to 1.12 becomes 2.24 sigma. So that'll be 2.24 sigma. Let me go get a sigma. There it is. So if R naught is 1.12 sigma, that means 2 R naught would be 2.24 sigma. So we look up 2.24 on this chart. 2.24 would be somewhere around here. And we're kind of just estimating from this graph, but we can do a reasonably close estimate. So 2.24 sigma, that's the actual distance we care about. And it looks like that is pretty close to 0. I think that's about -1 times 10 to the negative 21. So potential energy of one of those bonds is going to be -1 times 10 to the negative 21 joules. And note that that isn't epsilon. Epsilon is the low point, so 25 times 10 to the negative 21. This is just a small fraction of epsilon. Looks like about 1/25 of epsilon. But that's the potential energy of one of those AA bonds. And what do we need to figure out next? What do we need to do with this potential energy of one such bond?
Probably figure out what it is for the whole chain.
Yeah, we want to figure this out for the whole chain. And yeah, we'll get to the BB bonds next, but let's take a look at just the AA bonds for now. And then I think the BB bonds will be done almost identically, maybe even completely identically. But if we know the potential energy of one bond, we need to extend that to the whole chain by figuring out how many AA bonds are there. And for these purposes, we can ignore the B atoms entirely. We're just talking about the A atoms. And how many A atoms are there?
$50.
Yeah, we've got 50 A atoms. So if we're talking about the links from an A atom to the next A atom, and then from this one to the next, from this one to the next, from this one to the next, and so on. If we've got 50 A atoms, how many A to A bonds would there be? Yeah, it should be 49. The first A connects to the second A connects to the third A connects to the fourth A, and so on. But the 50th A doesn't connect to the 51st A because there is no 51st A. So there's only 49 bonds, or 49 bonds of this type. So once again, we can just multiply these. 49 bonds of this type times the energy per bond of this type. I should say all adjacent AA bonds. So that'll be just 49 times -1 times 10 to the -21st. So that'll just be -49 times 10 to the -21st joules. So that's the energy of all of the adjacent AA bonds. We're ignoring the A to like the next A over bonds, but those are so weak we can ignore them anyway. And it says only the bonds less than of separation less than or equal to 2 are not. Any questions on those AA bonds? And what about the BB bonds? Would those be any different? Should be about the same, right? And if we just consider this B to that B, this B to the next B, this B to the next B, it's still all the same bonds. There's still 2 are not apart from each other. It looks like, according to this graph, AA connections and BB connections use the same potential energy graph. So each one of those BB bonds is still going to be -1 times 10 to the -21st joules. We've got 50 B atoms, so we're still going to have 49 bonds. So we can say that really should be identical. If we take a look at the B to the next B bonds, it's all the same stuff. So the potential energy of all the adjacent BB bonds is also going to be -49 times 10 to the -21st joules. Because it's essentially the same structure. We've still got two B atoms separated by an A atom in between. Same distance, same potential energy graph, so we get the same result. So we now know the potential energy of all of the adjacent AB bonds, the potential energy of all the A to the next A bonds, and all the B to the next B bonds. That's all the bonds that we're considering here, all the bonds with separation less than or equal to 2 are not. So what do we do with those potential energy values? Yeah, we can just add those up. So we add together -297, and these are all times 10 to the -21st. This is why it's useful to leave them all as in the same format of times 10 to the whatever, rather than changing that around. That way we can just factor that out. So we've got -297 plus -49 plus another -49 all times 10 to the -21st joules. So that's 50 and 50, deduct 2 more, so 295 plus 100, so -395 times 10 to the -21 joules. So that would be the bond energy of the whole thing. This entire chain has a somewhat rounded off bond energy because we're ignoring the further neighbors. But a pretty good estimate is -395 times 10 to the -21 joules. Any questions on that? Without counting how many bonds there are, the problem is there isn't real, I mean, we need to know how many bonds there are so that we can figure out what to multiply the energy per bond with. Like we have the energy of one bonds, -297 or -49 or whatever, but you need to know how many bonds there are so you can multiply the energy per bond times the number of bonds of that type. Why are they negative? The thing is, the way we set this up in the first place, we define 0 as the energy of no bond at all. If bond energy is 0, that means we've broken the bond. So a negative energy means that they're bonded. Or to put it another way, if you've got atoms that are just whizzing around and not bonded to each other, you have to remove energy to get them settle down to a bonded state. So 0 bond energy means they're not bonded. You'd have to remove energy, taking it down to the negatives, in order to make them bonded. What equation? I mean, in a sense, we are kind of using an equation here. We're taking number of bonds of that type times energy of one bond of that type. So in a sense, it is kind of an equation. It's just that the equation is just multiplying energy per bond times number of bonds. And there may be different ways of finding how many bonds there are. But in this case, since I mean, just if you just got a chain of atoms, I think that's straightforward enough that you can just not so much manually count it up. We didn't like count from 1 to 99. But it's often useful to look at a smaller, simpler version of the same problem. Like you wouldn't want to have to draw out 100 atoms and count the number of bonds manually. But if you can draw out maybe 6 atoms and count up, oh, there's 5 bonds, and maybe draw 10 atoms and count, oh, there's 9 bonds, then it becomes pretty clear that the pattern is 1 bond less than the number of atoms. And you can also sort of reason your way through that. You can say the first atom has a bond to the next atom. The second atom has a bond to the next atom, and so on, except the last one does not have a bond to the next atom because there is no next atom. It's not really a universal method. It's more like you take a look at the cluster of atoms that you're dealing with. If it's a very small sample, like maybe just, I don't know, 5 or 10 atoms or something, you can actually draw out the bonds manually and make sure you've got all of them. If it's a very straightforward type of cluster, even if it is very large, like even if this was 1 million atoms, we could still say the number of bonds is 1 less than the number of atoms. For more complicated arrangements, you would need more complicated calculations. But it still goes back to the same idea of figure out how many bonds of that type there are and multiply by the energy per bond. Any other questions on that so far? Okay, let me pause this and take a quick look at those solutions you sent, just so I can see if they're actually doing anything differently. Yeah, it looks like they're doing essentially the same thing, but using an equation to estimate the number of particles or number of bonds. The thing is, I wouldn't really use an equation like that in this case because we can just figure out how many bonds there are without an equation. We can say in a chain like this, there's 1 less bond than there are atoms. But more generally, if you can figure out how many bonds there are associated with a typical atom, you can take number of atoms of that type times number of bonds per atom. But if that double counts, you would have to divide by 2. In this case, though, we're not double counting. We know there's 99 bonds of the AB type, and we know there's 49 bonds of the AA type or the BB type. Any other questions on that one? And let's see if we can apply the same sort of approach to this other cluster that's 2-dimensional. Move these to the side in case we need them later. Actually, I don't think we're going to need these. So in this case, if we wanted to figure out some information about these 2 clusters. In this case, well, in part A, we were dealing with 100 atoms. And we said that those 100 atoms had 99 bonds. If we had been using an estimate, though, if we had looked at this in terms of each particle individually, let's say we're looking at particle A. How many bonds does that particle have? If we're talking about, let's say, bonds from A to the AB bonds that we were looking at in the first place. Yeah, that atom has 2 bonds to its nearest neighbors. If we take a look at the next atom, let's say this B atom, because we can basically treat A and B interchangeably since they're behaving pretty much identically here. This B atom also has 2 bonds to nearest neighbors. And then this next atom has 2 bonds to nearest neighbors. One to the left and one to the right. So we can say that each atom has 2 nearest neighbors. If we wanted to calculate using a formula how many bonds there are, we could say each atom has 2 nearest neighbors. Let's say 2 bonds. And how many atoms are there in total? Yeah, 100 atoms. So what can we do with the 2 bonds and 100 atoms to figure out the number of bonds in total? If we have 2 bonds per atom and we have 100 atoms, mathematically, how would we combine these 2 pieces of information in a useful way? Yeah, we could multiply those. And take a look at the units there. If we multiply two bonds per atom times 100 atoms, what happens to the units? Bonds per atom times atoms, what happens to the units there? Yeah, atoms cancel out, we're left with just bonds. So this should tell us the total number of bonds, except for 2 slight problems. If we're saying this atom has 2 bonds, and this atom has 2 bonds, and this atom has 2 bonds, what are we doing as we count up those bonds? Yeah, we're counting each bond twice. So what do we need to do to account for that? Right, divide by 2. So 2 bonds per atom times 100 atoms total, divided by 2 to eliminate this double counting problem, and we get 100 bonds. Is that the actual number of bonds we were talking about earlier? How many AB bonds are there actually? Yeah, in that chain of 100, we had 99 bonds. So why didn't this calculation give us the exact number of bonds? Why did this provide 100 bonds instead of the correct answer of 99 bonds? Why was that off by 1? Where did that mistake come in? We're assuming that every atom has 2 bonds. Does every atom in this entire chain actually have 2 bonds? Yeah, those atoms on the end, the edges here. Exactly, this equation is ignoring the edge effects. There's 100 atoms, all the ones in the interior, the second one, the third one, all the way up to 99th one, do have 2 bonds. But the very first one only has 1 bond, and the very last one only has 1 bond. So this equation overestimates the number of bonds, only very slightly. It's only off at the edges. So in this case, it's only predicting 1 more bond than there actually are. But 1 out of 100 it's only 1%, but this means our answer will be off by 1%. And also, if this was a much smaller cluster, like if we only had, let's say, 5 atoms, then the equation would predict five bonds, but there would only be 4 bonds. So that would be off by 25%. So for small clusters, edge effects are pretty significant. And you should take those into account by considering how many bonds there actually are. But for very large clusters, the edge effects are pretty small compared to the total number. So the equation should be a pretty close estimate. And in part B, it's talking about not just 100 atoms, but a mole of atoms. So 600 sextillion atoms, a huge number of atoms, which means the edge effects are going to be insignificant. There's a lot of atoms on the edge, but those are very small amount compared to the enormous number of atoms on the interior. So for very large clusters, you can completely ignore edge effects without any problems at all. So that's what I would do in these cases. I mean, it would be a nightmare to try and count up the bonds individually. So instead, you create equations to predict how many bonds you should expect. So let's try that out here. Let's say starting with the rectangular grid, this grid of all these at right angles. In this rectangular grid, and note that we still want to predict based on any particle pairs with center-center separations less than or equal to 2 R naught. So let's say in this grid, let's say we're talking about some central atom. And these are all type A atoms, so we don't need to worry about AA, BB, AB. They're all just AB atoms. If we take a look at some central atom, how many nearest neighbors would you say that has? Yeah, 4 nearest neighbors, 1 above, 1 below, 1 to the left, 1 to the right. And note that this is because this is 2-dimensional. If this was 3-dimensional, there would be more in front and behind. But in 2-dimensional, in a rectangular grid, it's just 1 above, 1 below, 1 to the left, 1 to the right. So we've got 4 nearest neighbors per particle. Four per atom. But how do we convert that to the number of bonds like that in the entire cluster? Yeah, we can multiply by the total number of atoms, which is how much? How many atoms are there in this entire cluster? Yeah, we're talking about a mole, so that's going to be Avogadro's number of atoms. So 4 times Avogadro's number. And does this approach double count? Yeah, and if you're not sure, you can check by taking a look at another atom nearby of the same type. Like this is a type A atom, which has 4 nearest neighbors. This one is also a type A atom. It also has 4 nearest neighbors, 1, 2, 3, 4. And right there, I can see that I'm double counting. I just counted this bond twice. And this is going to happen if I look at some of the other neighbors as well. If I say like, this is a type A atom, and it has 1, 2, 3, 4 nearest neighbors. I just counted that bond twice as well. If I keep going, I'm going to count every bond in the whole system twice. So I need to do what? How do I account for that? Yeah, a 1/2, or just divided by 2. So 4 times Avogadro's number divided by 2 is 2 Na bonds total. Note that again, for the units, atoms and atoms cancel out, so we just get bonds. So this would be the total number of nearest neighbor bonds of this type for this entire cluster, 2 times Avogadro's number of bonds. This is ignoring edge effects. Realistically, the actual value will be slightly less than that. But 1 mole of atoms is enormous. This is a colossal number of atoms. So the edge effects would be so insignificant, we can ignore them completely. So we now know the energy, or the total number of bonds is 2 times Avogadro's number. And also, how would we figure out the energy of one of those bonds? Because we want to multiply the number of bonds times the energy per bond. So where can we find the energy of one of these bonds? Yeah, those are R naught apart. We can go back to the graph and look at R naught, which is the 1.12 sigma. In other words, the lowest possible energy. And since these are AA bonds, we look at the AA graph. Looks like that is -25. That is the equilibrium distance has an associated energy of -25 times 10 to the -21st joules. So the energy of each one of these is 25 times 10 to the -21st joules. 25 times 10 to the -21st. Actually, I should say -25, because the energy of a bonded pair is a negative value. So we've got 2 times Avogadro's number of bonds. We have this much energy each. And now we can just multiply those. Energy per bond times number of bonds. In fact, you could even think of this in terms of units as this much joules per bond. Multiply number of bonds times number of joules per bond, and we get the total number of joules. So multiply those 2 times Avogadro's number, 6.02 times 10 to the 23rd, times -25 times 10 to the -21 joules. And we can combine the 10 to the 23rd and 10 to the -21 to just get 10 squared. So that's 2 times 6.02 would be 12.04 times -25 times 10 to the 23rd times 10 to the -21 is just 100. So about 12 times 25 would be what, 300? So -300 0.04 times 0.25 would be 1 times another 100. So -30,100 joules. Yeah. So that is the bond energy of all of the nearest neighbor AA bonds. Any questions on that so far? Or we could just say -30.1 kilojoules. And those aren't the only bonds we want to consider, though, because it says all the bonds with center-to-center separations less than or equal to 2R naught. So what other bonds do we need to consider here? Like if we want to go just a little bit further away, let's say we're starting at the same central atom. Which direction could we go to get to another atom that's a little bit further away? So which direction would we go to get to those second nearest neighbors? If we want to get to another atom that's a little bit further away from this than these ones are, which direction could we go? Yeah, if we go on the diagonals, let's say just up and to the left, how many neighbors of that distance do we have? Yeah, it looks like 4. Up and to the left, up and to the right, down and to the left, down and to the right. So those are all of the neighbors of that distance. And what is that distance going to be? The negative is to account for the fact that a bond has a negative amount of energy. So we're including that negative here. The energy per bond is a negative value. So either way, you're still just taking the number of bonds of this type times the energy per bond, which is a negative value. And I would recommend thinking about this not in terms of memorizing an equation, but just in terms of finding the total amount of energy by multiplying energy per bond times number of bonds. Yeah, square root of 2, because this is a diagonal on a 45-degree. In fact, you could even use Pythagorean theorem to do this. We know these two sides are equilibrium distance R naught. So if you use Pythagorean theorem, R naught squared plus R naught squared, then take the square root. This is going to be square root of 2 times R naught. So that distance, second nearest neighbor distance is 2 times, or square root of 2 times R naught. In other words, square root of 2 times, what was that, 1.12 sigma? Yeah, the R naught distance was 1.12 sigma. So if we multiply square root of 2 times 1.12, square root of 2 is about 1.4 times 1.12. So we're getting about 1.5, yeah, 1.58 sigma. So once again, we can take a look at the graph, consulting the graph of potential energy, but now instead of looking at 1.12 sigma, we're going to look at 1.58 sigma. So going back to this graph, you can probably get this now. Going back to this graph, we have 1.58 sigma. So something like here. I guess that's 1.5, 1.6, so a little bit before 1.6. That looks like pretty close to -6 times 10 to the -21st. So based on the graph, I'd say 1.58 sigma is associated with an energy approximately -6 times 10 to the -21st. So each of these has energy -6 times 10 to the -21 joules. That's the energy of one of those diagonal bonds. Any questions on that so far? And now that we've got the energy, we just need to figure out how many bonds of that type there are. We know there's 4 per atom. And I think we can take the same approach. We have 4 per atom, 4 bonds per atom. Times, and we're still dealing with 1 mole, so Avogadro's number of atoms. And now let's check if this double counts. If we're claiming that this atom has 4 second nearest neighbors, what if we take a look at another atom nearby? Let's say this atom. Can we say this atom has 4 second nearest neighbors? Keeping in mind, there's another row up top. So we've got 1 up and to the left, 1 up and to the right, 1 down and to the right, 1 down and to the left. And it looks like we've just double counted that. In fact, if we try applying this to all the atoms nearby, we're going to be double counting every bond. So since we're double counting all the bonds, we do need to divide by 2. So 4 bonds per atom times Avogadro's number of atoms divided by 2 to eliminate double counting is 2 Na bonds of this type. And we just figured out that's -6 times 10 to the -21 joules of energy per bond. So again, we can multiply those together. Number of bonds times energy per bond. So potential energy of all these bonds is going to be 2 times Avogadro's number times energy per bond, -6 times 10 to the -21 joules per bond. So that's, again, the 10 to the -23rd, or 10 to the 23rd and 10 to the -21 works out to times 100. Then we've got 2 times, well, 6.02 times 6 would be 36.12. Times 2 would be 72.24. And then with the negative as well. So that's -7,224 joules. Or if we convert to kilojoules by shifting the decimal point 3 spaces, negative 7.224 kilojoules. So that's the extra bond energy associated with all these second nearest neighbor bonds. Any questions on that calculation so far? Also, how does that compare to the bond energy from the nearest neighbor bonds? It is much less, but not a whole lot less. It's what, about a fourth of it? So we wouldn't really want to ignore this. We want to include this because this, I mean, negative 30.1 kilojoules is a very rough estimate. It's missing an extra fourth of the same amount. So the negative 30.1 kilojoules would be a very rough estimate. That plus this, so negative 37.324 kilojoules would be a much better estimate. So the total so far, add those together, negative 30.1 plus negative 7.2 is negative 37.324. I'll just round that off to negative 37.3. We don't really want to claim a whole bunch more accuracy than we really have. But about negative 37.3 kilojoules. So our nearest neighbor's only estimate is missing a whole bunch of it. Negative 37.3 kilojoules is much more accurate because we're including the nearest neighbors and the second nearest neighbors. Any questions on that so far? So let's see if we can make this even more accurate. Are there any other bonds that fit the center-to-center separations less than or equal to 2 R naught that's required here? Because the diagonals we were looking at were 1.4 R naught, square root of 2 R naught. What if we go a little bit further out? What's the next distance we hit? Or which direction can we go to go a little bit further than this diagonal? By the way, one approach that I find often really helps is if you draw out like an expanding circle. Like if you imagine you've got a circle centered at the atom you care about, and you slowly expand that out, you're going to hit some cluster of nearby atoms, specifically these 4 adjacent atoms. Those are the nearest neighbors. If you then continue expanding outwards from there, so that same expanding circle, if that expands outwards little by little, the very next atoms you hit are going to be these second nearest neighbors. So these 4 along this ring, those are the second nearest neighbors. If we expand that out further, let's say we've got, we start with the same size circle we have so far. If we take that circle and expand it out further, little by little, it looks like the very next atoms we hit are this one to the left, this one to the right, and also if we fill in the extra rows, one directly above and one directly below. So those would be the third nearest neighbors. And any other diagonal is going to be a little bit further than that. Note that that goes outside the circle, because the circle is just all the points equidistant from the center. So all the points on the circle are the same distance from the center, the central atom we care about. So all of the atoms that are intersecting that circle are all equidistant from that central atom. So I find that visualizing an expanding circle like this is a very useful way of figuring out which atoms do I need to include in the next cluster of however many nearest neighbors. Any questions on the geometry there so far? And I think the numbers are going to be a little easier for this because we don't even need to worry about diagonals and triangles and stuff. How far is it from the central atom out to this second nearest neighbor? Or I guess the third nearest neighbor, I should say. Yeah, that's just 2 times the equilibrium distance, because we're going equilibrium distance to the nearest neighbor plus an extra copy of the equilibrium distance. So distance is just 2 R naught, in other words, 2 times 1.12 sigma, that is 2.24 sigma. And I think we already checked the graph for that, right? When it was 2.24 sigma, that was what, -1 times 10 to the negative 24th. So if we need it, we can get that again by checking. This was, yeah, -1 times 10 to the negative 21st. So that's the energy of one of those bonds. So that's each one has energy -1 times 10 to the negative 21st joules. And it looks like we should also have the same number of them, 2 times Avogadro's number, because there's 4 bonds per atom. There are Avogadro's number of atoms. We're still double counting, so we still need to divide by 2. So there's 2 Na bonds of this type at -1 times 10 to the negative 21 joules each. Multiply those, and that'll tell us the bond energy of all of those of that type. So 2 times Avogadro's number times -1 times 10 to the negative 21 joules each. And here we just got, again, 10 to the 23rd and 10 to the negative 21 becomes 100 joules. And then 2 times 6.02 times -1 would be -12.04. In other words, -1204 or -1.204 kilojoules. So that would be the extra contribution from just those third nearest neighbor bonds. And note that this is even smaller than the contribution from the second nearest neighbor bonds. So this makes the total a little more accurate. Add in the extra -1.2, we get -38.5. So we've gotten a little bit more accuracy. But note that that was kind of a lot of work for just a little tiny bit more accuracy. And we could go to the fourth nearest neighbors going on some of the other diagonals, but that would be an even smaller amount of extra energy for a lot more work. So the further out you go, the less useful, the less extra utility you get from the extra work. So usually nearest neighbor bonds and second nearest neighbor bonds is close enough for most purposes. Third nearest neighbor bonds adds a little more accuracy, which is sometimes useful. But in this case, we're now talking about bonds that are 2 R naught apart from each other. So that's as accurate as this problem is asking for anyway. Any other questions on that? So ultimately what we would say is the bond energy of this entire mole of atoms would be -38.5 kilojoules, which means you'd have to add 38.5 kilojoules to do what? What would happen if you take this cluster of atoms and add 38.5 kilojoules of energy? What happens when you add enough energy to raise Ebond all the way up to 0? Yeah, the bond breaks. Or specifically, +1 epsilon is enough to break 1 bond. The total bond energy, if we raise that all the way up to 0, we've broken all the bonds. So adding 38.5 kilojoules would be enough energy to vaporize the whole thing, breaking all the bonds, turning the solid into a gas. And since that's the amount of energy to vaporize exactly 1 mole, we could also call that the delta H per mole. So we can say for this substance, delta H vape mole, I guess it's really delta H of sublimation, since we're going from solid to gas, is 38.5 kilojoules per mole. So we say this is the molar heat of sublimation. Delta H being the standardized, the amount of energy to vaporize it, standardized to exactly 1 mole. Any questions on that? Or any other questions on particle model of bond energy in general? The reason we call this sublimation is because if we're breaking all the bonds, we're going from solid directly to gas. Going to a liquid would mean breaking some of the bonds so the particles are able to move around, but they're still attached to each other. So melting would mean breaking some of the bonds, but allowing them to still be bonded, but moving around a little bit. Boiling would be going from liquid to gas, so breaking the rest of the bonds. But if you're starting in solid form, very bonded, and then breaking all the bonds at once, that would be sublimation. And this is kind of a simplified model in the sense that we're ignoring the transition from solid to liquid and liquid to gas. We're just going straight from solid to gas. Realistically, there are other things going on where adding enough heat breaks some of the bonds so it's able to move as a liquid, but then you have to raise the temperature before you can break the rest of the bonds and make it a gas. In this case, we're just assuming it's going straight from solid to gas. To get some more practice on this, I'd recommend running through part 2 on your own, where you've got a similar structure of 1 mole of atoms, but they're in a hexagonal grid instead. So go through the same process, figure out how many adjacent atoms there are, that's the nearest neighbors, and then figure out which direction would you have to go, again, using that expanding circle approach. Figure out how many second nearest neighbors there are, and then continuing how many third nearest neighbors until you get to a distance of 2 R naught. Delta H for vaporization would mean, technically that would be going from liquid to gas. Sublimation is going from solid to gas. But we might often describe this as vaporization anyway, because we are technically vaporizing the solid. We're turning it into a vapor. But usually when we talk about vaporization, we mean going from a liquid to a gas. But I think it should be pretty clear from context. Like if you already start as a solid and you're turning it into a gas, and the problem asks about vaporizing, presumably that's talking about turning whatever you have right now into a gas. So yeah, try out the same approach for the hexagonal grid. You should get some slightly different results because you've got different numbers of nearest neighbors and different distances based on the diagonals. If you're not sure, draw out triangles and experiment with the Pythagorean theorem until you can find those missing distances. But I'd also like to take a look at part 2 here when it's talking about heat capacity. If we're dealing with heat capacity in a case like this, how would you figure out information about heat capacity? That is, how it responds to heat being added to change the temperature. First of all, how do we define heat capacity in the first place? What does heat capacity mean? It's going to involve modes, yes. Although that's not really part of the definition. It's just that the definition ends up resulting in having to do with modes. Formally, heat capacity is a ratio of how much heat you add divided by how much the temperature changes as a result. I generally think of heat capacity as like a cost per degree Celsius, how much heat it costs to raise the temperature a certain amount, or you could even think of it as a difficulty level. A very large heat capacity means it's very difficult to change the temperature. A very small heat capacity means it's very easy to change the temperature. And the reason it's called heat capacity is that it can kind of be thought of as how much excess heat, well, really how much energy, how much thermal energy the object can store per degree of temperature change. So if we want to figure out what's the heat capacity, we need to figure out how the amount of heat added or removed relates to how much the temperature changes. And let's say you add some heat to change the temperature. What kind of energy are you changing? What kind of energy does that count as if it's associated with the temperature change? Yeah, that's thermal energy. And if we're talking about constant volume, there's no work being done, so all the heat goes directly into thermal energy. So in general, if there's no work, that is only heat, then heat is delta E thermal. Usually we'd write delta E thermal equals heat plus work. But in a constant volume case, there's no work being done. Also, this is a solid, so I wouldn't really expect it to expand or contract anyway, at least not a significant amount. So we can assume all the heat goes directly into delta E thermal, which means if it's heat capacity at constant volume, then heat is just delta E thermal. So heat capacity at constant volume can be defined as delta E thermal over delta temperature, which also means delta E thermal will always be heat capacity at constant volume times delta temperature. And that's true no matter what type of process it is. Even if you're dealing with a process where volume is not constant, the change in thermal energy is always going to be what the heat capacity would be at constant volume times the change in temperature. However, in this case, we're assuming the volume is not changing anyway. Do you have a formula for delta E thermal, or somebody mentioned modes earlier? How does delta E thermal relate to number of modes? Yeah, if you take 1/2 kBT, that's the energy per mode. Boltzmann's constant over 2 times temperature, that's the energy per mode. And then we can multiply that by number of modes if we want energy per atom. And this also is essentially a unit conversion thing. We've got energy per mode times modes per atom. Modes and modes cancel out, we're left with energy per atom. But we're not dealing with just one atom here, we're dealing with how many? Yeah, a mole. So if we want to convert this to energy per mole, we'd multiply by number of atoms in a mole, Avogadro's number. So this is, and again, this is like unit conversion. Energy per mode times modes per atom, so modes and modes cancel out, times atoms per mole. So atoms and atoms cancel out, we're left with energy for the entire mole. And if we had several moles or some fraction of a mole, we could also multiply this by number of moles to get an actual formula for total thermal energy. In this case, though, we happen to have exactly 1 mole. Also, it looks like we have here Boltzmann's constant times Avogadro's number. What convenient substitution can we use here? Yeah, that's just R, the ideal gas constant. Anytime you see Boltzmann's constant, which is very, very small, times Avogadro's number, which is very, very large, you can replace that with R, the ideal gas constant, which is about 8.31 joules per Kelvin mole. So let's do that. If we make that substitution, we get energy per mole is Kb times Na is R, times temperature, times number of modes. It's number of modes per atom. I'm just going to write it as number of modes here, divided by 2. Though what we really care about for heat capacity is delta E thermal. So let's apply a delta to both sides. Delta energy per mole. And of all the stuff on the other side, what's the only part of the other side that's actually changing as we add heat? Yeah. So we're going to have a delta on the temperature. All the other multipliers are constant, so they can be pulled out of the delta. So it looks like energy per mole is just R times delta temperature times number of modes per particle divided by 2. If we were talking about for a larger or smaller sample, we'd also have times N, times number of moles. But in this case, we can ignore that because number of moles is exactly 1. So that's our formula for delta energy for the entire mole. Any questions on that so far?
Yeah, so in the equation in the middle where it says E per mole equals Kb divided by 2 times T, we have number of modes per atom, and then it just says number of modes in the next one. Is that also per atom or per? Okay.
Yeah, this should still be number of modes per atom, or more generally per particle. It might be per atom, per molecule, per whatever particle we're talking about. I'm just going to abbreviate it as number of modes, but that still means number of modes per atom.
So if it was like a diatomic gas, then we would have to divide that or change that.
In that case, I would write it as number of modes per per molecule. So let me just change
Okay.
it. Number of modes per particle. That's really what we care about.
Thank you.
And that might be atoms, it might be molecules, whatever particles we're considering at the moment. So yeah, number of modes per whatever type of particle we care about. And if we substitute that back into the original heat capacity here, we can replace delta E thermal with this whole formula. So let's write that out. CV equals, and I am going to actually include N here. N times, so N, little n here is number of moles, times delta T, times number of modes, divided by 2. That whole thing divided by delta temperature. And I'm including the little n here so we can generalize this, just in case it's not exactly 1 mole. In this case, it is, so we can always fill in 1 later. So the delta energy for the whole thing, let me just say delta E thermal is N times R times delta T times number of modes over 2. This, by the way, I think is one of the most useful formulas for delta E thermal. As long as you're dealing with a substance where you know something about the number of modes, this is an extremely useful formula. Especially because what else, or where else have you seen NR delta T? Where else does nRT show up? Yeah, this shows up in the ideal gas law. So another very useful substitution you can make, if you're talking about a gas, which is not the case here, these are solids, so this won't work. But if you're talking about a gas, you can make this substitution. Say delta E thermal equals NR delta T becomes delta PV. And there's a delta there because it's not just T, it's delta T. And then we still have number of modes over 2. So the really nice thing about this is it provides a formula for delta E thermal that does not rely on knowing the temperature at all. As long as you know the pressure and volume at the beginning and the pressure and volume at the end, delta PV will just be P final V final minus P initial V initial. And as long as you know the number of modes, you can calculate the change in thermal energy without needing to know anything about the temperature. So this version is especially useful if you're dealing with an ideal gas and you know the pressure volume graph. Then you can just read pressure and volume initial and pressure and volume final directly off the graph and calculate it from there. But the NR delta T times number of modes over 2, this works no matter what phase it's in. The pressure volume version only works for a gas, but for a gas, it is an extremely useful variant. Any questions on that formula so far?
Yeah, so for the delta P times V, that's just, is it delta P times delta V?
No, that doesn't actually work, because if you write out, like we're talking about delta the whole thing. So delta P times V, that would mean the final value of the whole thing minus the initial value of the whole thing.
Oh,
That's not actually the same as change in pressure times change in volume. Because if we wrote that out, delta pressure times change in times delta volume, that would mean P final minus P initial times V final minus V initial. If you multiply that out, you'd have to use the distributive property, which would mean you'd be multiplying P final times both V final and V initial. So you get P final V final minus P final V initial. And also the negative P initial would be multiplied by both V final and negative V initial. So you get minus P initial V final plus P initial V initial. And note that these are not the same result. Delta P times delta V is very different from delta PV.
okay, thank you.
So delta PV is definitely the one that we want. And that's really why we put this in parentheses. This is, the parentheses here are to emphasize, take the final pressure times volume and the initial pressure times volume, and then subtract to find the difference. So let me emphasize that with crossing this out. This is not the way to do it. This one is the way to do it. And again, that's really only relevant for a gas. But again, it's a very useful formula if you're dealing with a gas, especially if you're working with a pressure volume graph, because you can just read initial and final pressure and volume right off the graph And as long as you know number of modes, you can directly calculate delta E thermal. Or in reverse, if you know the delta E thermal, you can solve for number of modes. And that gives you some useful information about, for instance, what type of molecule you're dealing with, what the shape of the molecule is, for example. So let's try going back to the CV formula, the heat capacity at constant volume. We've got our formula for delta E thermal and our delta T times number of modes over 2. Based on the definition of heat capacity, we're dividing that by delta temperature, because we're looking at the energy cost per degree Celsius of temperature change, or per Kelvin. If we divide those, though, what's going to happen? Yeah, the delta T cancels out. We've got times delta T in the denominator, and also a delta T in the numerator and denominator, so they cancel out. So all that's left is number of moles times ideal gas constant times number of modes over 2. So that is the constant volume heat capacity. Cancel out delta temperature. And that's it. The constant volume heat capacity of any substance is number of moles of that sample times ideal gas constant times number of modes per particle divided by 2. And that holds true no matter what substance it is, no matter what phase it's in, no matter what process it's going through. The heat capacity at constant volume is always N times R times number of modes over 2. Whereas the heat capacity at constant pressure would be that much plus an extra bit. The extra bit happens to be N times R. In this particular case, though, how many moles are we dealing with? Yeah, for this sample, you got 1 mole times, I should actually include the units there, 1 mole times R, which is 8.31 joules per Kelvin mole. And what about number of modes? If this is a monoatomic solid, how many modes per atom would you expect? And why 4? Why not the usual 6? Yeah, this is only 2-dimensional. So if you count up the number of modes, each atom, usually we'd expect 3 translational modes, 3 kinetic energy modes, because it can move in 3 dimensions. But if this is a 2-dimensional solid, that atom can only move in 2 dimensions, left and right, up and down. So it's got 2 translational modes. It can also interact with its neighbors in 2 dimensions, its neighbors to the left and right, its neighbors above and below, because this is only 2-dimensional. So we really only have 4 modes, 4 modes per particle. And we've also got this divided by 2, which ultimately came from the 1/2 kb in the original formula. So putting that all together, we've got, and at this point we could call this CV per moles, or CVM, because it's the heat capacity per mole at constant volume. So moles and moles cancel out, we get, actually I guess if we are calling it C mole, we should include the per mole. But that looks like 8.31 times 4 divided by 2, so that's 16.62 joules per Kelvin. So this sample has a heat capacity of 16.62 joules per Kelvin. Or alternatively, you could just say 2R if you want to leave it in terms of R. And again, that represents the difficulty of changing the temperature, that it costs 16.62 joules of energy per Kelvin that you want to change the temperature. Any other questions on that? Yeah, go ahead.
Can you explain how you found the 4 moles again?
For the number of modes?
Yeah, or the number of modes, sorry.
Yeah, for the number of modes, in a monoatomic solid, in reality, we would usually expect 3 translational modes because the atom can move in 3 dimensions, and also 3 vibrational or 3 potential energy modes because the atom can interact with its neighbors in 3 dimensions. In this case, though, this is 2-dimensional. So each atom has two translational kinetic energy modes because it can only move in 2 dimensions, and 2 potential energy modes because it can only interact with its neighbors in 2 dimensions, neighbors to the left and right, neighbors above and below. So add those up, you get 4 modes per atom.
So I don't know if this is possible, but if for some reason they said like 1 dimension, we would only have 2 modes.
Yeah, because that atom can move in only 1 dimension. So that's 1 kinetic energy mode. And it can interact with its neighbors in 1 dimension. So that's 1 potential energy mode.
Okay, thank you.
And of course, if it's a gas, it would not have those potential energy modes because it doesn't have any nearby neighbors to interact with. But a 2-dimensional gas doesn't really make much sense anyway. Yeah, the CP equation, we found that CV is N times R times number of modes over 2, because we were assuming that CV is delta E thermal over delta temperature. If we take a look at constant pressure, though, things get a little different. Let me clear out a little bit of space here to make room for that. So let's investigate constant pressure. In other words, an isobaric process. And this really only matters for a gas, because if we're talking about a solid or liquid, the volume is not going to change significantly. But for a gas, if you hold the pressure constant and heat it up, the gas is going to expand, or cool it down, the gas is going to contract. We can still go back to the original definition of heat capacity. Heat capacity is heat over delta temperature. That is how much heat it costs per Kelvin of temperature change. For constant volume, we were assuming no work, so heat could just be replaced by delta E thermal. But if the volume is changing, heat is not equal to delta E thermal. Because if the volume is changing, what else is happening? There's not just heat, there's also what else? Yeah, there's also work. So delta E thermal is heat plus work, which means heat is going to be delta E thermal minus work. If we fill that in for the definition of heat capacity is going to be delta E thermal minus work divided by delta temperature. So heat capacity in general is not going to be delta E thermal over delta temperature. It's delta E thermal minus work. That is however much is heat left over divided by delta temperature. It just so happens that in a constant volume process, there's no work at all. So we just get delta E thermal over delta temperature anyway. So, and the amount of work can be kind of flexible depending on what kind of process it is. But if we're specifically assuming constant pressure, that becomes a lot more predictable. What is the usual formula for work if the pressure is constant? If you just got a flat line on the PV graph, what's the amount of work? Yeah, pressure times delta volume. And also with the negative sign, because if the volume's increasing, then you have a negative amount of work. If the volume's decreasing, you have a positive amount of work. So negative pressure times delta volume. Substituting that in for work, if we replace work with negative P times delta V, then when we subtract work, we're really adding P delta V. So heat is delta E thermal plus pressure times delta volume. And a very useful way to think of this is if you have some container with a piston that's able to rise and fall, let's say you add some heat. That heat is going to make the gas heat up. It's going to raise its temperature, but also it expands, pushing up the piston. So when you add heat, some of that heat goes into making the gas get hotter, raising the temperature. But some of that heat also is sort of lost in making the gas expand. Not all of the heat goes into raising the temperature directly. Some of it goes into making the gas expand instead. So that means it's going to be more expensive in terms of heat cost to make the temperature rise. You've got to add not only enough heat to raise the thermal energy, but also enough heat to make the gas expand the right amount to follow the ideal gas law. So we should expect the heat capacity at constant pressure to be larger than the heat capacity at constant volume. It's more expensive to raise the temperature because we also have to account for the work leaving the system. So let's make that correction. Heat, instead of writing it as just C equals heat over delta temperature, we can replace heat with delta E thermal plus P times delta V. So it's still heat. It's just we're splitting up heat into how much heat goes into raising the temperature versus how much heat is lost as work, making the gas expand. Any questions on that so far? And then algebraically, we can split this up. The divided by delta temperature distributes to both of these terms being added together. So we can say the heat capacity is delta E thermal over delta temperature plus P times delta V over delta temperature. Now, I should probably write this as CP also, because we are now talking specifically about heat capacity at constant pressure. And some useful substitutions we can make here. Where have you seen delta E thermal over delta T before? That's just CV. Yeah, that's exactly the CV we were just looking at. So we can actually make a substitution here. Where we see delta E thermal over delta T, that is the constant volume heat capacity. So that means CP is just CV plus an extra little bit. So this is what I was saying earlier about how the constant pressure heat capacity is a little bit more than the constant volume heat capacity, in the sense that constant volume heat capacity is how much it costs to heat up the gas. Constant pressure heat capacity costs a little bit more because you're not only raising the gas's temperature, you're also losing some energy to the expansion. So that little bit more is P delta V over delta T. But we can figure out a substitution for that also, because what other equation also relates pressure, volume, and temperature? Yeah, once again, we can always go back to the ideal gas law. Pressure times volume equals N times R times T. Let me make that a little more visible, actually. Let's say dark red. If we apply a delta to both sides, because we have some deltas involved here, we'll have to apply a delta. Applying a delta to both sides. And usually we'd expect this delta PV to be P final V final minus P initial V initial, which it is. But what do we know about pressure in this particular process? What were we assuming about pressure here? It's constant. Yeah, I wouldn't say it equals 0 because it still has a pressure. It's just that the pressure is not changing. So the final pressure and the initial pressure are the same. We don't really even need the sub F and the sub I. It's just the pressure. And if it's the same pressure, what can we do with that times pressure? What can you do with the same multiplier in both terms? It's not going to cancel out because we don't really have anything else to cancel it with. But you can factor it out. Factor out pressure and you get what's left. Yeah, the change in V. V final minus V initial, which is exactly delta V. Another way to put this is that a constant multiplier can be pulled out of a delta. Delta constant times V is equal to constant times delta V. Likewise, if we were talking about constant volume, but the pressure changing, we could factor V out and get V times delta P. But in general, any constant multiplier can be factored out of a delta, because delta is just talking about subtraction anyway. Meanwhile, on the other side of the equation, what is constant on the other side of the equation? What's not changing? Yeah, so we can factor out N times R times, and then we just have delta temperature. So pressure times volume is going to equal N times R times delta T because pressure is constant. If we make that substitution, if we just replace pressure times volume with nR delta T, but then we divide that by delta T, what's left? Yeah, N times R. So that's the little bit extra. Constant pressure heat capacity is constant volume heat capacity plus a little bit extra. We now know what that little bit extra is. Number of moles times ideal gas constant. So that represents the extra energy it takes on account of the expansion. You're adding heat not only to raise the temperature, but also to expand the gas because you are allowing the volume to change. It's just that constant pressure makes that predictable, makes the amount of work predictable. So we can make a very, very precise formula. And also, what would be a very useful standardized number of moles to use? If you could choose any number of moles to use, what would be the easiest number of moles? Yeah, let's say exactly 1 mole. If we standardize this to exactly 1 mole, we get the molar constant pressure heat capacity equals the molar constant volume heat capacity plus 1R. And likewise, the molar constant volume heat capacity, that's just what we found earlier, N times R times number of modes over 2, but with N being exactly 1, that'll be just R times number of modes over 2. So if you're talking about exactly 1 mole, the constant volume molar heat capacity is R times number of modes over 2. The constant pressure molar heat capacity is that much plus an extra R. In other words, R times number of modes over 2 plus an extra R. So that's how you can calculate the molar constant volume heat capacity of any substance. And well, specifically a gas we'd usually be talking about, and the molar constant pressure heat capacity of the same gas. How much heat per degree Celsius it takes to raise the temperature if it's at constant volume versus how much heat per degree Celsius if it's at constant pressure. The energy change per degree Celsius is the same no matter what process it is. But if you're specifically talking about heat capacity, that's talking about heat per degree Celsius of temperature change. So that depends on what process it is, since heat is path dependent. Any other questions on heat capacity?
How did you know that CVM equals R times number of modes over 2 again?
That was from what we were doing over here with the, ultimately just from the thermal energy formula.
Okay.
The thermal energy, starting with the idea of energy per mode being kb over 2 times temperature and scaling it up from there. We ended up with delta thermal energy can be written as nR delta T times number of modes over 2. And then if you divide that by delta temperature, you're left with just N times R times number of modes over 2. Then if you standardize that to exactly 1 mole, you just get 1 times R times number of modes over 2. So that's the constant volume molar heat capacity. Any other questions on that? Number 2C on practice final 5. Yeah, let me pull that up. Practice final number 5. So what's going on here? We have this cluster, this sort of hexagonal grid structure. And it gives us some information on energy up here. We probably want that later. So we've got a 1 atom thick solid. So basically just a 2-dimensional grid here. And several different types of atoms. So if we want to look for the nearest neighbor bonds only, AB and AA, because notice that the type, I think the type B atoms are the white ones and the type A atoms are the sort of brown bronze one. Yeah, that's what the key says down here. So there are no nearest neighbor BB bonds. There are no B atoms that are adjacent to other B atoms. And this is saying only consider the nearest neighbor ones anyway. So if you look at a typical, let's say a typical type A atom, let's say this one. How many type A nearest neighbors does it have? Yeah, looks like just two. This one, and let me make that a little bigger. We've got a nearest neighbor over here and another nearest neighbor A over here. There's also the type B nearest neighbor, but we'll have to consider those separately because it's a different amount of energy per bond. So it looks like each type A atom has two nearest neighbors. And how many type A atoms are there? According to the paragraph above. Yeah, 6 moles. We have 6 times Avogadro's number type A atoms of that type. And each one of them has 2 bonds of this type. And now we need to check, are we double counting? If we take a look at another, and note that we're talking about type A atoms here. If we take a look at another type A atom nearby, let's say this type A atom, we can also say that has 2 nearest neighbors that are type A, this one and this one. Have we counted a bond twice? Yeah, so that means we are going to need to divide by 2. We're not always going to be double counting. And I think the reason why might become apparent when we get to the next type of bond. In this case, we definitely are. If we say this type A atom has 2 bonds and this type A atom has 2 bonds, we've counted that bond twice. So 6 times Avogadro's number times 2 divided by 2 would just be 6 Na bonds of this type altogether. And then we can multiply by the epsilon for that type, which I think was given up here. Where was it? Did it tell us about A's and B's here? Oh, write your answer in terms of epsilon AB and epsilon AA. So we actually can just leave it in terms of that as a variable. Let me copy that. Yeah. Okay, so that means each one of these bonds has an energy of negative epsilon AA. So the energy of all those bonds is going to be negative epsilon AA times the number of bonds of that type, which looks like 6 times Avogadro's number. So 6 times Avogadro's number of bonds of that type times the energy per bond, which is negative epsilon AA. And note that this is still number of bonds of that type times energy per bond of that type. So there's not really a need to memorize specific formulas. It's really more about building formulas as you go, depending on what's going on and what information you need. So I would generally just think of it in terms of figure out how many bonds there are of that type and multiply by the energy of one bond of that type, which is typically going to be negative epsilon or negative some fraction of epsilon. Any questions on those AA bonds so far? Then let's take a look at the AB bonds. Let me clear these from the diagram. There are a couple of different ways you could go about this. One way would be to consider the A molecule or the A atoms and the B atoms are linked to. Like, let's say we take a look at an A atom. If we look at one typical A atom, how many AB bonds is it connected to? Yeah, just one. So if we think of this AB bonds in terms of the A atoms, we can say there's still 6 moles of A atoms, 6 moles of A atoms times, and then there's 1 bond of that type per atom. And then to check for double counting, let's take a look at another type A atom nearby. Here's another nearby type A atom. How many AB bonds is that connected to? Yeah, also just 1. Note that we haven't double counted anything yet. Or let's say we take a look at another nearby type A atom. Let's say this type A atom. That's also connected to 1 AB bond. Or let's say this type A atom is also connected to 1 AB bond. Or maybe this type A atom is also connected to 1 single AB bond. Are we counting any of these bonds twice as we go through the A atoms in the region? No, we're not actually double counting. This bond got counted only once. This bond got counted only once. This bond got counted only once. Each one of these bonds from A to B is getting counted only once. So we're not actually double counting. We've got 6 moles of A atoms. Each one is connected to 1 bond of the type we're considering right now. And that doesn't double count. So we wouldn't divide by 2 in this case. So the energy of all those would be negative epsilon AB. That is the energy of one of those bonds times the number of bonds, which is 6 moles times 1, not divided by 2. So 6 Na. And we could also do that. Let's try a different approach. So try looking at the A atoms, we could say each A atom is connected to 1 B atom. But separately, let's look at this from the perspective of the B atoms. If we consider 1 B atom, let's say the AB bonds from B perspective. As opposed to what we were doing before, which was from A's perspective. Let's say we consider a single type B atom. Let's say this one. How many type A atoms is it connected to? Yeah, connected to 3 type A atoms. And if we try another one nearby, we could say, let's say this type B atom is connected to also 3 type A atoms. But we're not double counting because the B atom is not connected to the other B atom. So there's no double counting to worry about. We can just multiply number of type B atoms times number of bonds per atom. And how many type B atoms are there in this entire sample? Yeah, it tells us up here in the paragraph, there's 2 moles of type B atoms. So 2 Na B atoms times how many bonds per atom? 3 bonds per atom. And we weren't double counting here, so we don't need to divide by 2. So multiply that out. We get, oh, and also we need the negative epsilon AB as the energy per bond, times then 2 Na times 3 is 6 times Avogadro's number. So we still get the same number of bonds regardless of which way we write it. You could look at the AB bonds from A's perspective, or you could look at the AB bonds from B's perspective. It still leads to the same result. However, you would only use one or the other of these. You don't need both of them because you just need to count the AB bonds once. So the total bond energy of this entire sample would be negative epsilon AA times 6 moles plus negative epsilon AB times also 6 moles. So that should be the energy of the entire sample. Any other questions on that? All right, looks like we are out of time. So keep studying, keep practicing this stuff. I will be checking in on Discord periodically throughout the weekend, so feel free to ask me any other questions there. Good luck on finals, and I will see you next quarter.